Okay. So I guess you will send us the slides of the last lecture.
Yeah, this is the last slide.
Yes. So, okay. So please, Timoteo.
Okay. So welcome, everybody. Thank you for attending this second lecture. So I already asked one question. If you have other questions, please do not hesitate to raise them now or while I'm speaking, just raise your hand or open your micro and ask a question. Okay, so it's a lecture, it's not a talk or... Okay, so this is the last slide of last time. And so the idea was that I show you the existence of this limit cycle, but I prepare a slightly more simple example to be sure to show you what I'm talking. So I also change my, last time I use, say not PowerPoint, so the PowerPoint by Macintosh, and now I use this good notes to see which is the best one for my future lecture on at distance. Okay, so I decided to show you this model, which is called Stewart Landau oscillator. It is a bit different because it's a complex model. So now Z is a complex variable. So you have a real part X and the imaginary Y. And you have also two parameters, A is a real number and B is a real, you can think of positive number. And so this oscillator, it describes a complex amplitude, which is Z. And so it has a modulus and an argument, so an exponential part. And the idea is to study this oscillator. Of course, because you can write Z as X plus I, Y, you can use so the real variables, and you end up with this real two-dimensional system. So I think I can do easily. Okay, it works. So I can do the computation for you, but it's very straightforward. So you have Z dot is equal, so Z A, okay, is right at the same time than me. Oh, sorry, I just forgot the equation. Minus Z square, and Z is equal to X plus I, Y. And so if you differentiate the definition, so you have Z dot is equal to X dot plus I, Y dot, and this is equal to X, so X plus I, Y, A plus E, I, B, minus the modulus of Z is X square plus Y square. And then you perform the computation, so you develop the product, and you identify left and right members, complex and pure complex and pure real. So you have X dot is equal to X times A, and then you have I, Y times I, B, so it is minus Y, B, and then you have X times the square, so minus X times X square plus Y square. This is the only one. And then you have the complex part. So you have Y dot is equal. So you have X times IB, so XB, Y times A, so YA, and then you have minus Y X square plus Y square. So it starts forward just to bit warm up. So you have this equation, and now that you have a two-dimensional real system, but you can recognize that the origin is an equilibrium. Because if you put x0 and y0, then everything is 0. So you have x dot equals 0, y dot equals 0. And so you want to study the stability about this point. So if you remember what I told you last time, you have to compute the Jacobian matrix, which is the matrix of the derivative of the vector field, say x dot to y dot, with respect to the component xy. So if you do the, and you should evaluate this on the equilibrium, so on 0 and 0. So if you do this, so the derivative of x dot with respect to x is a, and then this is okay. Let me write it, but at the end it will not intervene. Minus 2x squared. Then you have to, so let me remove this one. So then you have to take the derivative of x dot with respect to y. So this is minus b minus 2xy. Then you have to take the derivative of y dot with respect to x. So it is b minus 2 times xy, and then the derivative of y dot with respect to y. So this is a minus x squared plus y squared minus 2y squared. And evaluate everything on 0, 0, 0. And so if you evaluate on 0, these terms goes to 0, this one goes to 0, this one goes to 0, this one goes to 0, and also this one and this one. And so at the end, let me add in 1. So you end up with y is equal to a, is the minus is over there, so minus b, b, a. And so you have to compute the eigenvalues of this matrix. So you have to compute j minus lambda identity equal to 0. So you have to compute a minus lambda minus b, b, a minus lambda determinant 0. But this is a minus lambda to the square plus b to the square equal to 0, which means a minus lambda to the square is equal minus b square. So I remember I assume that b is positive. So this means that a minus lambda is equal plus minus ib. That is lambda is equal a plus minus ib. So the eigenvalues of my matrix J are a plus minus ab. And if you remember, the origin is stable if the real part of lambda is negative, A is unstable if the real part is positive. And so here you end up with the condition, so the real part is A, this is the real part. So if A is negative, you have stability. If A is positive, then you have instability, okay? The point is that, okay, so the check already did, sorry. So this was there, so you have proved that it's stable or unstable. But working on the real variables is not so easy to understand what happened when you have instability. And but the point is that you have this term there, y squared plus x squared, that looks like a circle, of the radius a circle. So you can use this idea and introduce polar coordinates. And this is what is done here. So instead of working in a Cartesian coordinate, you use a polar coordinate in the complex plane. So now z is its modulus, rho of t, times exponential I theta of t. And then I will show you that now the equation of motion are really easier at this one. So just let me do the computation again. So you have, oh sorry, you have your equation, z dot is equal to z times a plus I minus modulus of z. And now you are writing z like rho a e I theta. And then you differentiate z. This gives you rho dot a I theta plus I e I theta dot. And then you plug this information inside the equation. So you rho a I theta a plus I b minus, and the modulus of z now is just rho square. Okay, so you can observe that you can simplify the exponential of both sides. And again, you factor terms that are real or pure imaginary. So in the real part, you have rho dot is equal. And so on the right-hand side, the real part is given by rho times a minus rho square. While the imaginary part is given by rho theta dot on the left, while on the right, you only have sorry, no, without I. So you only have B rho. Okay, so this is the system that I showed you before. And so the first equation has for sure two solutions: rho equal to 0 and rho equal to so rho is positive because it's the to square root of if A is negative, you don't have this second solution. But plus b times t. So theta is indeed a frequency, is the angular frequency of the motion. And then you see that rho is a constant equal to square root of a. And so indeed, so the check, sorry, I lose my, okay, so I have to write, to do by hand. So if you look in the plane rho theta, yeah, you have the case a smaller than 0, and so here so let me rewrite again. Rho dot is equal rho a minus rho square, and so if you have in this case, so the origin is stable, but you observe that a minus rho square is negative. So this quantity is always smaller than rho. So this means that whenever you start in the complex plane, you shrink to the origin. So everything shrinks onto the origin. At the same time, it rotates around by some speed bt. So if a is negative, we are doing spirals towards the origin. So the origin is the stable global attractor. While if a is positive, now you know that you have two solutions, rho equal to 0 and rho equal square root of a. And square root of a, taking into account that beta is still equal to b times t, is a circle. Sorry. But we also proved that the origin is unstable. So what the system does is spiraling outward the origin, reaching this circle from inside. If you look from outside, if you start with a rho larger, so rho square larger than a, this quantity is negative again. It remains negative as long as rho square is larger than a. So this means that if you start outside the circle, you are still spiraling, but towards the limit cycle. And so we prove that we have a limit cycle which is globally stable, only one moreover. So this is isolated because it's the only one. And so in this case, the system, you pass from a single stable point here to an unstable point plus a limit cycle. So if you want, you can draw a diagram like this one. If I put now here I'm on parameter a, and here if you want rho of the position of the equilibrium. When a is negative, you have a stable point, which is the origin, rho equal to 0. When a is positive, the origin is still there, but it's unstable. So let me draw with a dashed line. And at the same point, you have this square root-like solution. So this is the square root of a, but you have to think that indeed it is like a limit cycle. So it's more like something like this. So this means that the solution here, they all converge to the fixed point, while here they converge to this limit cycle. And so we have proved that using this bifurcation, you can create the limit cycles. Okay, so now I would like to discuss a bit this idea of bifurcation, because I think is an idea is very useful also in the following. And so a bifurcation, roughly speaking, is once you have a dynamical system depending on a parameter, a in our case, then if you move your parameter, at some point you can reach a critical values for which you have a qualitative change in the behavior of the system. So qualitative is not a precise definition, but you understand from the picture that I show you, qualitative in this case means that you have a single fixed point that bifurcates into a limit cycle plus again another unstable fixed point. So the shape of the dynamical system or the portrait phase change qualitatively. So this is the idea of bifurcation. So let me show you a few examples of bifurcation that can exist. So I took all the examples from the book by Strogatz that I quote the last time. So if you want, I will send you the slide at the end. So the simple bifurcation is this saddle node bifurcation. So I present the result in the case of one-dimensional systems, but of course the same results are valid more or less in all dimension. And I also write the simplest system that exhibits this kind of bifurcation. This is called a normal form. So this system here is called normal form. So this means that you can have a much more complicated system which has this saddle node bifurcation, and then you can change locally variable in such a way the system can be always rewritten in this way. That's what does mean normal form. So what happens in this saddle node? Well, of course, as the name say, you have a saddle and a node. So a node is a stable fixed point. A saddle is an unstable fixed point. So this is so this is a node, and it is stable because if you start a bit to the left or a bit to the right to the node, you converge to the node in a one dimension on the line, while this is my saddle. Indeed, once you start close by, you go away in both sides. Okay, but then you move your these points can be determined by putting x dot is equal to 0. That means r plus x squared is equal to 0, and because r is negative, you have x equal plus or minus square root of minus r. Okay, so these are the two equilibria. But then if r is equal to 0, you see from the definition that the two roots coincide to the same point, which is 0. And so here you have an half unstable node, because from the left you converge to the point, and from the right you go away from the point. So it is a point which in some sense is unstable because you pass through, but it's just for the values of r equal to 0. And once r is larger than 0, then geometrically you see that your parabola will no longer intersect the x-axis, so you don't have any fixed point. And indeed you can see that you cannot have this root because r being positive minus r is complex, so you don't have the point on the real plane. And so you pass from a system where you have 2 points stable, one stable, one unstable, that once you move the parameter, they collide and then they disappear. So the saddle node is the disappearing of 2 equilibria. You have another situation which is called, okay, this is just an example of what is called with a more, say, I don't know, fancy name, blue sky bifurcation, because it's as before, but in the opposite direction. And you have 2 points, in this case, that appear out of the clear blue sky. So you have your model, which is with r negative, and then once you move up to 0, you have something is happening. And then when r is positive, you have these 2 points that appear from nowhere. Okay, it's the same as before, just that you did in the opposite direction. You first have 2 points that disappear, but it's just sometimes you can find this name blue sky bifurcation. But it's just a saddle node bifurcation. Okay, then the next one is a bifurcation is called transcritical, where now the 2 points they always exist. So you have again one stable and one unstable. So again, here we have my stable, which is the origin. And if you start from the positive side, you go to the origin, and you start close enough to the negative side, you also go to the origin. And then you have this unstable that I draw in white, which is unstable because if you start close by, to the left, you go away, and also to the right, you go away. And so the normal form is given now by this equation. And you realize that if you write this as x times r minus x, that you have x equal 0, which is a root, and x equal r, which is the second one. So you always have 2 equilibria. One is 0 and the other is r negative in this case. Once r is 0, the 2 equilibria do coincide. You are in this case over there, where again, you just pass through the origin. And once r is positive, then you still have 0 as an equilibrium, but now it becomes unstable. While the other equilibrium, which is now x equal to r positive, is stable. So in some sense, you have 2 equilibria that collide and pass through. This is a bit the idea. You have one equilibrium here stable. Then if you continue, it becomes unstable, while the other one that were unstable, it becomes unstable. So it's an exchange of stability between 2 equilibria, but they do exist all the time. So previously, you have two equilibria and then they disappear. Now you always have two equilibria. They just exchange the stability. The next one is a bit more interesting because now you increase the number of equilibria. It is called supercritical, if you want, a pitchfork bifurcation. So pitchfork because you remember a fork, more or less. So if you think this is a fork. So supercritical because you create two stable new equilibria. There's two. You will say you can also have the subcritical pitchfork bifurcation where you have two unstable equilibria. Okay, and so this is the normal form. Again, if you factorize x, you have r minus x squared. And so x equal to 0 is always a solution because it's a factor. And then the other solution is x equal plus minus r if r is positive. While if r is negative, you don't have the second solution. So this means that if r is negative, you are here, you only have the origin, so x equal to 0, which is stable. You can prove again by computing the derivative and showing that it's negative. So everything is attracted to this point. But once r becomes positive, then 0 is still a solution, but you can prove that now it's unstable. And so if you start close to the origin, you will go away. And then you have these two new solutions plus minus square root of r that you can prove they are stable. Just again, do the derivative and evaluate on plus minus square root. And then they are stable because they attract what is close by. If you prefer a more geometrical view, if r is negative, this function, which is a cubic function, intersect the x-axis only at the origin like this way. So you only have one intersection, of course. So if r is 0, you have a tangent in 0. While if r is positive, now the cubic has this shape. So you have three intersections. And then you can prove that one is unstable and two are stable. So now is a bifurcation where you have initially one stable point that bifurcate into two stable and one unstable. So you create something from nothing. And so as I said, there is the opposite, which is the subcritical. So the important point is not that this is subcritical and this is supercritical because if you want to, the fork goes in this direction or here the fork go in the other direction. So you can have a supercritical also if you have another parameters and the fork is like this. This is still a supercritical because supercritical refers to the point that you have, say, more point than before, more equilibrium than before. Okay, so the subcritical is called subcritical because these points are unstable now. So the idea is really as before. The normal form is very similar, but now you have a sign plus in between r and x squared. And so the other root, so you have x equal to 0. And the other root is x equal plus minus square root of minus r exists only if r is negative. In this case, you can prove that if r is negative, then the origin is a stable fixed point. So you are attracted to the origin, while these two roots so you push away from the you can put x equal to 0. So you have this kind of system. Okay, so this is the other pitchfork bifurcation. So you can find this too. Again, I insist that this is a normal form. This means that you can have a very different system, but once you have a good set of coordinates, so you have a good change of coordinate, you can only put on this form is a supercritical, and the other form is supercritical, subcritical. So this is really in the neighborhood of the parameter space where you have the bifurcation. Alors, so the subcritical has this point. So let me go here. So I told you that the square root point is unstable, but also r, so x equal to 0 is unstable if r is positive. So this means that if you take this system system, except condition is inside this region, all the conditions blow up to infinity. Because if you are there, you are above the, or if you go down and so on. So if you use this system, indeed your system is not very interesting because all the solutions blow up except the one that are inside. So once you have this kind of subcritical pitch for bifurcation, it's good to ask which is the next leading term. Is it some, of course, should be a power larger than 3. So I assume that is x to the 5. So what it matters is the coefficient in front, if it's plus or minus. If it is minus, this means that if you draw now the position of the equilibrium, you can find that you have this shape where the initial one is this shape, which is the pitchfork subcritical, which is there. So this part here. But then, because of the 5th power, you have these new 2 branches. You can prove by just computing the derivative or compute the solution of the 4th order equation, it can be done, that they are stable. So this means now that if you start for R positive, you are pushed away to x equal to 0, but you are catched by this solution here and here. If you start very, say, above, you are again attracted toward the solution. So you no longer have this kind of blow up solution. And the same is true if you start with R, which is, say, small, because now you are attracted to this branch of the stable. What is interesting here is that you can have this kind of hysteresis phenomenon. It is the following. If you start with some parameters, say, I don't know, here. So your system, so if you start with your R here, and you start your initial condition there, your system converges towards this equilibrium because it's stable. If you slightly move the parameter R, so your system, and you start again close to the previous one, or again here, your system moves close by. So actually you are following this branch, okay? But once you arrive at this RS and you decrease again R, there is no longer this branch stable. And so the only existent stable point is the one x equal to 0. So suddenly your equilibria jump from this branch down to the solution. So if you are still decreasing R, you are moving to the left with R equal to 0. But the important point is that if you now instead you increase R from here, you will still remain on the x equal to 0. So you don't jump again to the previous solution. And you remain on x equal to 0 up to this value, say 0 in my case, where the 0 solution there is called ferromagnetic, where if you store a current in a piece of iron, then you have this kind of magnetic field which is created. So this is the same idea, but the point is that you have your system, you continuously change a parameter, your equilibrium continuously change up to some point there, and then you jump to a new value. Okay, but if you go back to your parameter to the value, you will not follow again the same path, but you follow another path. So this is a phenomenon which is quite frequent. It is called also hysteresis. But so it is related to the subcritical pitchfork, but you need this correction term because otherwise everything blow up. Okay. Okay, the next one you already spoke about is called Hopf bifurcation. This is the example that I show you in the case of the Stewart Landau example. If you recognize, so here is the case B equal to -1. This was my B. My previous equation was, so I called a rho instead of R. It was A minus, so it was, if you want. So this is the equation that I had before. It's exactly the same. And so here is this kind of a picture where if your parameter, which is called, so in my picture, mu, is negative, everything converges to 0. While it's positive, you have this kind of convergence to the limit cycle, spiraling inward and outward. Okay, so the example that I show you to create a limit cycle for the for the Stewart Landau model is an Hopf bifurcation. So is one of the most used bifurcation method to create a limit cycle. Okay, so I will go on this point. The last point, so if you remember last time, we started by speaking about so fixed point. Then we pass to the case of periodic point. And now the last point that I will just very briefly introduce you is the case of chaotic system. So chaotic system or chaotic dynamical system is again a huge research domain. So I'll just give you one rough definition. There's the following. A system can be said to be chaotic if it is very sensible to initial condition. What does it mean? It means that you, for some given initial data, you have your orbit. So I say this is my orbit, okay, because I start from this point. Then you slightly change the initial point. So you add some small delta if you want, so of delta 0 at time 0. And then you look how this new orbit bifurcate with respect to the previous one. So this is the new orbit, which is just, I can say, x plus delta. The system is chaotic if this distance grow fast in time. Growing fast means growing exponentially. Indeed, if you take the logarithm of the distance between the two orbits, you divide by t. So this is the exponent of your potential exponential growth. This means that if you do this, okay, delta grows more or less like exponential lambda t. So this is the maximal Lyapunov exponent. You can prove that it almost everywhere exists with respect to the initial condition. You can prove that indeed there are more than one Lyapunov exponent. And so if lambda is positive, you have a chaotic system. If lambda is negative, the system is not chaotic, but you can still have, so if lambda is 0, sorry, the system can still be chaotic, but you don't have the exponential growth, but you have a power law growth. Okay, but to be more precise, you need more than this to be chaotic, because of just divergence. You take the solution, you take the system x dot is equal to x. Of course, the two nearby solution diverges exponentially, but it is not chaotic at all. You can predict the future. So you need indeed that the orbit remains in a bounded domain, because if they blow up, it's not interesting at all. So chaoticity means that you have high sensitivity to initial condition, but also orbits to belong to some bounded region that indeed is called chaotic attractor. Okay, and so this opened the way to the measure theory supported by the attractors. So, but I have no time to speak about this point. I just show you two pictures that are two main examples of chaotic system that maybe you already see somewhere. So the Lorentz one is this butterfly effect. You have an almost linear system except for this x times y part. So it is non-linear, and then this x times z. And so these two terms are enough to create this strange behavior where you have your point that can do certain number of loops one side of the butterfly, and then suddenly jump to the other side, do another number of jump or turns, jump back and forth. So this is a system that can put in relation with the shift. Indeed, you can ask, is the system on the right butterfly or on the left? You can show that you can put the Lorentz system in a bijection with a shift left and right, so something which is completely chaotic. On the other hand, we have this Russell system, which is interesting because the attractor lives in the space where all the coordinates are positive. So if you're interested in, I don't know, ecology with animals or biology with bacteria or chemistry with concentration of stuffs, the Russell system is a good toy model because you can prove that at chaos, but with positive quantities. So X is positive, Y is positive, and Z is positive. So they can really represent say, real stuff. Why in the Lorentz system, you pass through negative values. So you cannot use the Lorentz system to study, I don't know, ecology, for instance. Okay. So this is the part on dynamical systems. And I will now start the second part on network theory. The last time, except if there are some questions on the dynamical system part. No question? I don't see the chat, so Stefanelli, if you see the chat, just
yes. No, there are no questions. No
questions. Okay, okay. So Okay, so I go on with the network part. So I already showed you last time there's two books, the books by Barabashi and the book by, say, Newman and Barabashi. There are many books on complex network. I often use these two in my research or in my lecture. This one by Vega Redondo, which is complex social networks. So it means that it's inspired by social networks, but indeed is a complex network book where there are inside epidemics, diffusion networks, and so on. And this is this more recent one, complex networks, which is more recent application. There are algorithms. There is also a GitHub related to the book where you can download a databases. You can download a program in C, I think also in C or maybe in R, I don't remember exactly, where there are all the code that are in the book are provided. So I think it's a very good book because you also have by side these tools to use it. Okay, but again, if you Google complex system, complex networks, you find a lot of books. So what is a network? So we are speaking about network theory. So what is a network? So as I told you last time in the introduction, a network is just a bunch of nodes, say units that are linked together. And so you can have some kind of non-physical networks. It can be friendship. So the nodes are person and the links are friendship relation. Or you can have the www, where the nodes are the web pages and the link are the hyperlink. So the fact that you click on a page and you go to another page. This is not physical. There is not a wire behind, but you just jump from one hyperlink to the other. Or you can have email, text, calls, and so on. So where you have a person or a robot that sends something which is virtual because it does not really exist except for the electron if you want. Or you can have the physical networks where you are really power plant, where the nodes are the power plant and the links are really the wire. So the connection are physical connection that link physically to nodes. Or the internet, where you have the nodes are the routers and the links are the cable, the Ethernet cables that link to routers. Or you have the transportation like road, train, flight, where say in the case of road, the link can be cities, in the case of say a station, in the case of flight airport, and then the link are road, rails, and the flight, the path of the flight, okay? So you can have on very different kind of networks. So I show just this is the flight, the worldwide flight map. This is social patterns. There are a network that constructed for children at school. I think it's a school in French, where they attach to each child a RFID tag that allow to measure how long a child communicators in front of another. And so they reconstruct this kind of network. You have, of course, social networks that we are used to, Facebook, Twitter, and so on. You have protein network or gene network, where the nodes are the protein of the genes. You have a link if they do interact in some way. Or, as I told you, the power plant, where each node is a power plant. Then you have wire because you have this line, high voltage line. Okay. Okay, once you have this stuff, so you can understand it's a very broad definition. You can think so, as I already said, that you have these dots that are your basic units, and then you put just a line, a link among them. So in the jargon, the dots are called nodes, and that pairwise connected among them with a link of edge. You can change you can find both names is the same. And so as I told you before, A, B, and C can be humans. And then if they are friends, you draw a line between A and B. You can also draw a line between A, C, but B and C, they are not friends because you don't have a link among them. And so because they are friends, they can exchange idea. But for instance, B and C cannot exchange idea directly because you have to pass through A. The same is true if instead you are taking the www, where now you have A and B and C are web pages. The page A and B are linked, so there is an hyperlink. So a click, you can pass from A to B and vice versa. You can pass to A to C and vice versa, but you cannot pass from B to C. You have to pass through A. And so because A and C, for instance, are linked, they share common hyperlinks. I told you once you do some web search, you can go to A to C or to C to A, but not to B, just to give a rough idea. Okay, once you have a network, whatever is the kind of network, you can encode it with a matrix. It's called adjacency matrix, which is a binary matrix. So it's a matrix with zeros and ones that are size n squared, where n is the number of nodes. And so you put A, I, J is equal to 1 if only if I and J are linked. And then you can compute the degree of the node, which is the number of neighborhoods. So you just sum A I J over one column, and then you obtain the number of links that are connected to the node I. Okay, so in my example that I gave before, so assume that the ABC are 1, 2, 3, the index 1, 2, 3. Then you see that A is connected to B, so there is a 1 over there. A is connected to C, so you also have a 1 over there. So B is connected to A, so you also have a 1, and C to A. But B and C are not connected, so you don't have 1s here, but you have zeros. And if you count the degree of A is 2, because of 2 has 2 friends. So A are two friends, while B and C, they have degree 1 because they just have 1 friend over one connection. And so if you sum A, you end up with this, 2, 1, 1. Okay? Okay, so this is the simple case of a network, but in reality, in several applications, the links are not reciprocal. So this means, so in my example here, I say that A is connected to B, and B is connected to A. So A is a friend of B, and B is a friend of A. Or the web page A has a link pointing toward B, and B has a link pointing toward A. But it's not always the case. You can be, I'm your friend, but you are not my friend. Or I'm a web page pointing to you, but you are not pointing to me. And so in this case, you have directed network. So where you have Aij is equal to 1, if and only if there is a link from J to I. So pay attention, because in some book, they use the opposite assumption. So they define Aij equal to 1 if there is from I to J. So you have just to pay attention at the beginning of the book where there is the notation. But once you have this one or this one, everything is the same. But you have to know what you are speaking about at the beginning. Okay. So in this case, you have a direct network. In my example, so here I have A, which is point to B, A point to C. And now I add this link, B point to C. So again, if Aij is 1, if only if J is pointing to I, you observe that you only have 1 here and here because you have that A is pointing to B and to C, and you have a new one here because you have the B is pointing to C. Start forward. I will not insist any longer. The point is that if you have a direct network, now you have 2 kinds of degrees. You have the number of links incoming and the number of links outgoing. And so you have, in this case, the out degree, which is the sum, so the number of exiting links, so it's the sum on the first index, or the number of in degree, so the number of incoming link, which is the sum on the second index. So this is because I use this convention. So if in your book, they use the opposite, so they use I goes to J means that there is a link, then you have to exchange I and J, so the out degree and the in degree, otherwise you are doing some mistake somewhere. Okay, so okay, just a simple example. I compute the number, out degree of A is 2 because he has 2 friends. Out degree of B is 1 because B point to C, and C out degree 0 because nobody is outgoing from C, and the in is the same. Okay. Okay. Lastly, okay, in the case of friendship, it's difficult to measure how friend I am with you, but in the case of power plant or protein, you can have weight because you can have the voltage passing from for the plant A to the plant B, or in the case of protein, you can have the strength at which the protein A interacts with the protein B. And so in many applications, you can have that the matrix is no longer a binary one, but it's a real matrix. Normally the weights are positive number, but you can also have negative in case. And so you have a weighted matrix. And so you say that Aij is equal to S if only if they have a connection whose weight is S. So here I'm assuming that the the matrix is non-directed, so it's symmetric. So this means that also AJI is equal to S. But of course, you could have a case where you have a link point from J, say I to J, with some strength, a much larger one. So let me do it this way. So I don't know if you understand, but I would say that J is much more friend to I than I to J. So this is not reciprocate. Okay. In this case, you can show that there is equivalent of degree, which is called strength, which is now the sum, so the same formula, but now it takes into account the number of incoming or outgoing links and the strength, the weight. And so in this case, you see that AC has a strength 2, but also A has a strength 1 to B, and then now A has a strength 3, while C has strength 2 because there is this weight and so on. Okay, there is another way to encode a network, which is given by the incidence matrix. I will need in the following, so I will just put the definition right now. So it's again a 0-1 binary matrix, but now the size is m times n, where m is the number of links, while n is the number of nodes. So the adjacency matrix is a square matrix n times n. The incidence matrix is in principle rectangular matrix of size m times n, where if you want, you have to enumerate the matrix element using as one index a link, so E, and a second index a node. And so if your link is ij, then you have the element ei is equal to 1, the element ej is minus 1 because you are thinking that the link, even if the matrix is not directed, is going in this direction, but it doesn't matter really. You can exchange the link and the matrix will not change at the end. Or MEK is 0 because K is neither I or G. Okay, in the jargon, I is called the tail and J is called the head of the link. Okay, and once you have this matrix, okay, let's just show you in the previous example, sorry. So this is the example I just showed at the beginning. You have your initial network. Here is the matrix A that I showed you before. Now I put as the first line the link AB, as the second line the link AC. And so this element is 1 because the node A is the tail of the link AB. This one is minus 1 because B is the head of the link AB. Similarly, here 1, it is minus 1. What is interesting with this incidence matrix, that if you do the product M transpose times M, you change the sign, you find a matrix which is N times N. So it's something, if you look at it, it looks very similar to the adjacency matrix. Indeed, it is the adjacency matrix minus a matrix such that on the diagonal, you have minus the degrees. Okay, so if you have this incidence matrix, you can reconstruct your adjacency matrix just doing this product, changing one sign if you want, and remove the diagonal. Okay, this will be used in the following once we will have the dynamics on the network. Okay, so let me now show you some model of networks. The first one, in the sense that the first that
excuse me, can I just ask a short question? I didn't get if I can weight the edges when it's a direct network. When you have direction.
You can also, you can also weight in this case. So here you should define, for instance, IEJ is equal S if J points toward A. And then you can have, for instance, the IJI is equal to S prime if I points toward J. So yeah, of course, you can have a non-symmetric relationship between two links. Yeah. Okay, so I was saying that one of the first models is this one by Erdos and Reni, which is a random network. It's called GNP. So you have n nodes, and you consider all the possible pairs of links. So there are n times n minus 1 divided by 2 links. And with a given probability p, you draw a link among them. There is a second model which is called GNM, where m is the number of links. And so the two models are, say, statistically equivalent when n is large. So in the second one, you have to imagine that you have all the possible networks that have n nodes and m links. If you draw one according to the measure defined on the set, you end up with this kind of network. So this is just a definition. So you can show easily that the average number of links is given by the binomial n over 2 times p, because of course you have all the possible couples of links are given by n times n minus 1 divided by 2, but because I'm considering that it's symmetric. And then for each one of those, with probability p, you draw or not the link. So this is why the average number of links is this number. Here I show you the reference. I don't know if you can read it, but this is the original paper by Erdos and Reni, where they studied this network. So if you can see, it's quite old. So network science is a recent research topics, but the network, indeed graphs, exists since a very long time. The second interesting point, you can ask which is the probability that a randomly chosen node has some degree, for instance, k. And so if you define p of k, this probability, you can show that this is a binomial. So you have this, the first factor, then p to the k is indeed the probability that k times you draw the link, so that your node at degree k, because you want to be connected to k order, and 1 minus p to this n minus 1 minus k is the negative probability, that the probability that your node is not connected, so 1 minus p with the remaining nodes. Also, and so in this case, if you take n arbitrarily large, but in such a way that n times p is a constant, then you can show that this number, this probability, convert to the Poisson distribution. So where you have n times p to the k exponential divided by k factorial. So in some sense, the Erdos-Reni random network, if the number of nodes is very, very large, is indeed a Poissonian distribution. So the probability that a randomly chosen node has degree k is given by this almost Gaussian function. And indeed, this is the plot. If you define the average degree as the sum of pk times k, so the probability of having degree k times this number, so you do this sum, then you end up this function. This looks like, really likes to a Gaussian, because this Poisson distribution. Okay, so this means that in an Erdos-Reni random network, once you fix p and n, almost all nodes, if you want a large part of node, they have the same degree. They have the average degree. Okay, and so it's like the height of the person. They more or less, so you have this distribution. You have very few ones that are very far down or very far up with respect to the average, but the bulk, so the large part of the network or the nodes are in this part. So they only have almost the same degree. Okay, so the second example is the network is called Watt-Strogatz. This is again a random network. I show you this where is the randomness, but with a new property is called small world property. So this network has been introduced. I thought I put maybe in the next slide the references by Watts and Strogatz, but with the inspiration of social network. There is this phenomenon of small world has been shown in movies, in books, and this is inspired by this idea that if you count in terms of friendship or in terms of having shaken your hands or person that knows other person, you can ask, okay, how far I am from, I don't know, a very known person, say, I don't know, the president of Brazil. You say, very far because I'm in Europe, I never meet him, he's in Brazil. But indeed, if you think of it, it's not so large, because I live in Belgium, but for sure I shake the hand, or I met at once the rector of my university, with for sure he met at least once, or the king of Belgium, or maybe the first minister. who for sure at some meeting G20 or something meet Bolsonaro. So this means that with only 3 steps, I'm linked to Bolsonaro. So it's amazing. But you can do this with almost everything. You can think of friendship.
Maybe you should think of being linked for a better person.
Yeah, okay. I choose the one because you are. Yeah,
I think you can find many other better person to be.
Yeah, okay, but I can just change the last link and say, I don't know, Barack Obama. The distance is the same because my first minister for sure met Barack Obama at some meeting. So, okay, it's really the point. It's not really the point. So this means that in social networks, despite the very large, the huge size of the network, there are shortcuts. So you can go from one node to another node that you think is very, very far in very few hops. And this can measure by this idea of distance. So the network is not topology. You can embed the network on real space in the case of transportation, and then you can measure links with kilometers and so on. But in principle, it's not topology. And so you count distances with the hop, jump, number of links. And so you can count the distance between I and J by just counting the number of links. And then you have this average shortest path or geodesical path, which is the average of all the possible distances between two nodes. Of course, if you have a complete network, so where each one is connected to everyone else, the distance is 1. If you have a lattice, so imagine a square lattice where you are connected to your north, south, east, and west neighborhood, then you go like 1 over d, where this dimension of the lattice, so in this case, 1 square root of n. In the previous case, I didn't show, but in the Erdős-Rényi, you increase logarithmically with n, so you still have a larger size, but not so large. And so with using this idea, what's a Strogatz? Oh, okay, I need another stuff, sorry, before. You have also introduced the idea of cluster coefficient, which is also related to friendship. Normally, if I have 2 friends, the probability that they two are friends each other is quite high. So this means that if I'm a node and I take 2 possible nodes connected to me, the probability that they also have a connection among them is large. And this can be measured using this clustering coefficient. So this clustering coefficient is the total possible number of triangles, so persons that knows each other, and this is the actual number of triangles that exist in my neighborhood. Okay, so this CI measured in this point. How many friends of mine are really friends among them, among all the possible friendship that can exist? So if you take this very simple example, you take, say, node I, he has 4 friends, so the degree is 4, but indeed only 2 of them are friends each other. So this y is equal to 2, and so CI is 1/3. Indeed, you can build also this triangle, but it does not exist. You can build this one, but it does not exist. You can build this one, does not exist, and this one. So among all the possible triangles that exist, you only have 2 that gives you 1/3. Okay, and then you can average this number on the whole population, on the whole network. With these 2 ideas of length and clustering, Watts-Strogatz define this network. The idea is the following. You have 1 parameter, so 1 knob that you turn from p equal to 0 to p equal to 1. At the beginning, you have a regular network, so a lattice. Here I have an example which is a ring, where each node is connected to the first neighborhood, to the second one, and the third one. Okay, but then I start with this parameter p to take all the possible link and rewire. For instance, here I disconnect these 2 because these links now is this one. Okay, and so you do this for all the links in some, say, I don't know, in some direction. You're turning around, and with probability p, you rewire all the links. Okay, and if you increase p equal to 1, at the end you have an almost random network because with probability 1, you rewire all the links. Okay, at the same time, so here is your parameter that is changing from 0 up to 1. You compute 2 stuff. You compute the length, average length, and the clustering. You normalize with respect to the initial one, so once you have p equal to 0. And you observe that the length decrease quite fast. So this is a log-log scale, while the clustering stay constant and then also decrease. And indeed, there is this zone of parameters p, where you have a large clustering, but a small distance. And so this is the small world. So once you have this kind of network, given n, you have a range of p that depends on n, for which you have this phenomenon of small length or small distances, but high clustering. And so this is the paper where Watts and Strogatz proposed this is a Nature paper in 1898. So it's a quite well cited paper about this small world. Okay, okay, it's already 8, but we started a bit late, so I think I can go on 5 minutes more. Yes. So, okay, but in reality, the first network that I showed, the Erdős-Rényi, is not a real network, in the sense that if you take now a real network, this is a network. So here are 3 examples. The first one is a collaboration among actors, means that you have all the actors of movies, you draw a link between them if they play in the same movie. Or you have the www, so nodes are web pages, and there is a link if there is an hyperlink among them. And the third one is a power grid, so you have power plants that are connected by wire. Okay, so they are real networks. They are things that exist in reality. If you plot the probability that a node has degree k in log scale, you didn't find this bell shape like in the Erdős-Rényi, but you find this kind of decreasing law. But observe, you are in log scale, so they are power law in the sense that the probability p of k behaves like 1 over k to some power gamma, with gamma positive. Okay, because I'm in a log scale. So this means that if you think of friendship, there are a lot of persons, very few friends. So there are a lot of nodes whose the number k is 1, 2, 3. But there are few nodes, the hubs, I say, that have very large number of friends. The same is true for the www. There are few pages that are connected to the large number of other pages. I don't know, a very quoted journal, newspaper, or Google site, for instance, and so on. But the most part of the largest part of all web pages are just connected to 1 or 2 others. Or again, the power plant, there are few ones that are very central, and the most number of them are just connected to the one. So this means that these networks that have been introduced by Barabás and Albert, I will explain in a while as you can build it, are very fragile, because if you attack the hub, the central hub, so the actor or the friend, you attack him, you will destroy the network, because you remove a node but a very large number of connections. While in the Erdős-Rényi case, if you attack the most connected nodes, because there are many connected nodes, your network will not change too much. Okay, so there is difference between attacking the Barabás-Albert with by choosing who would be attacked, and the Erdős-Rényi one. Okay, so the idea of this model is again from sociology, if you want. The idea is that if you are new in a university or in a town and you want to make some connection, you try to connect to people that are most known. And so the idea is that you start with a bunch of nodes, say M nodes, that are connected among them, and then each step you add a new node. So a new person enter in the town or the university. And this person can draw one link toward the one that already are there. But with whom? But the idea is that this new node will choose the node I with the probability is proportional to this degree. So the larger is the degree of I, the more probable is that the new node is connected to him. So this is a feedback loop, because if I get nodes, then Ki increases, and then we'll get more and more nodes. Okay, so this is the paper, is a science paper in '99, and where they introduce this model and they study some property. And what is interesting that you can explicitly compute the probability pk in this case, and in the limit of n large, this probability is exactly 1 over k to the power 3. And so this power law behavior that I showed before is exactly this one. So this is in the case of n arbitrarily large. Then I think a few years ago, there has been a quite strong debate on Twitter, mainly on the fact that does this kind of network really exist? Because, okay, I show you in the previous slide the power plant, but they are truncated at k equal, I don't know, 100, 1000. They do not truncate to infinity. Why? This power law exists for all k's. So in many applications, indeed, you have a cutoff. You have initially a power law, and then you have a cutoff because the network stops. It's not infinite. And so people start to understand or think about if this network do exist in reality or not. I think it's not a debate, but the point is that if you draw the power law for an Erdős-Renyi network or for this kind of real network, they behave differently. One is like a Gaussian, it is like this power law or log scale linear one. Okay, okay. One can generalize this behavior where you now put k is just 1 over k to the gamma. The gamma is a parameter larger than positive. It is called scale free. Scale free because there is no an embedded scale in the network as in the case of the Erdős-Renyi, where the best scale is the average degree. You can nevertheless compute the average degree. So it's not difficult because I have not time. So you have just to compute, say, the integral between the minimum degree of your network, say 1 or 2 or 3, and the largest degree of your network, I don't know, but it's a very large number, of what? Of again, k times pk in the k. So if now I write this more or less like integral between 1 and infinity, and instead of pk, I put 1 of k to the gamma, this is k times 1 minus gamma in the k. And then according to the value of gamma, so I say gamma is positive, but it's not enough, because if gamma is between 2 and 3, then you have the first moment, which is finite, but the second one is infinite. So this means that if you realize this network synthetically with a computer, then they will vary very much because the variance is not finite. While if gamma is large enough, then again, the average degree is finite, but also the variation is finite. So in this case, the network is more robust. You will obtain always more or less the same network as you change your replica. Okay, so I think this is the last, the two last. So if I can, so I start with the Erdős-Renyi, the small world, the scale free. But what if you start with any sequences of degrees? So you choose your sequence and you try to match up these nodes in such a way you obtain a network with this given sequence of degrees. This can be done. It's called configuration method. It is explained in the book that I showed you before, this complex network, where I told you there are also the algorithm available, and they provide this algorithm. Here's an example. You have 4 nodes, one which is degree 3, 2 degrees 2, and 1 degree 1. You have to try to connect these nodes, respecting the constraint on the degrees, and also to have a network at the end. And so you can have different cases. Here you have some that very simple, like this one, but some that looks like more a network. And so if you have a large number of nodes, it's more and more complex, and maybe sometimes you don't have a solution. So this is an heuristic algorithm that provides you the possible network. Lastly, once you have a network that contains 1,000 or millions of nodes, you cannot just draw them. You can also, it's also difficult to work on them. So for this reason, people thought of this idea of the TED community. What is a community? Is a bunch of nodes that are tightly connected among them. So think of a group of friends that have very few connections with other group of friends. So in a network, you can indeed divide your network into groups that are called communities, such that inside each community, you have a very strong set of connections, like in this one, in this one, and this one. But then you have a few connections among them. These are called weak links. So links, but they are important because without weak links, the network we disaggregate, we disappear because we split into several pieces. But they are weak. So this means that if you're interested in some process running on the top of this network, if you speak about some infection, if you start with this node which is infected, with high probability the infection spread among his friends, But with low probability, we spread across these links. But once the probability, so once the virus jumped to this one, then it will spread again to the other. So if you look to the time series, you will see something like the plateaus that are because the virus is, say, discovering new communities in the network. And so this idea of community is very important because in some sense it drives the dynamics on the network. Okay, so there are many algorithms to find the community detection. This is a well-established research domain. Again, we have a huge number of algorithms, some better than others, some capable to better determine some structure than others. But okay, if you're interested, we can speak next time or have a look of the book that I show you. Okay, because okay, I have no time to speak about community detection. Okay, so I think if you want, we can stop here because now we will start the first part with the dynamics on networks. That so can be maybe done next time. I don't know, it's up to you.
Yes.
Okay.
Yeah, as you wish. I had a question.
Yeah.
I was thinking about COVID and culture. And for example, the usual dynamics in the smaller city in Italy, no, I mean, not so small, but not so huge, will be the people meet with the family and they meet with always the same group of friends weekly. So will be more like this, what you were showing, you know, like they have their community and then sometimes they meet someone else, but they have more in this cluster. But then, for example, this is, it's different from Rio, where people meet a lot of people. They meet a person twice and then they, they meet other people. Here it's less clustered and more spread, you know, it's not so clustered. So I don't know if this kind of cultural dynamics have been studied with respect to COVID spreading because
yeah, it's a good question. So you are anticipating a bit of the next lecture in the sense that understanding how the network structure influence the dynamics is something that can be done. So for sure, there should be models, so synthetic model, I mean, toy models where people put an epidemic process on top of network, then change the topology, and they observe something different. This for sure exists. I don't know if people did this kind of result using real data. So they use a real data of friendship and they measure how a virus, COVID or other, spread in this kind of structured network. So I don't know, because in this case, you really need data where you know who is friends with whom. But the idea of the tracking, tracing, and so on is this, that once you find someone which is positive, you have to track and to trace all the friends in some sense, or the person that he met before, test them before, just the test person at random. But this is the idea. So saying that the virus spread more easily among the group or your friends in some sense, or the person that you meet more often, then it's best to check them before. But if you say that in Rio, the dynamics is completely different, this testing and tracing is not very effective, because then it's better to pick at a random.
Yes, it's more random, yeah. Because in fact, this was when they did the lockdown, you know, people locked down with their family. This is the initial. You observe that initially when you do the lockdown, you have an increase of infection because if in a family, people, I don't know, the parents and the children, they will not overlap so much as in lockdown. If there is one infect, of course, infect all the family. So in the short, so this is when you have a very clusterized. It's more you have a closer, how to say, a faster spreading in the small term within the cluster. But of course, then if you cut the link to the other cluster, then you might isolate the few clusters with the problem. Not so easy.
An interesting point is also, for instance, you think of children's school. The class is a very connected group of person, and then the spreading can be very high. So fortunately, young person do not spread so much. But anyway, if they go at home and school, they are the vehicle for the virus, or the university, or high schools also. Yeah, it's true that this kind of very tight structure can increase the spread of the virus, or it can be fashion, can be photos, can be whatever you want, but yes.
Yeah, but also on the other hand, the other extreme, the random spreader. we also can have someone that travels so much or moves so much, and it is infected.
Yeah, so this is another point. This is the point of the super spreaders, where which is an hub in the case that I showed before, is a guy which, because he met a very large number of persons, he has a very high probability to pass the infection. Yeah. So the infection is 2 times: is the number of persons you meet and the time you spend with them.
Yeah.
So if you meet only 1 person, but you spend all the day, the probability is high. But if you spend a few hours, but you meet 100 persons, the probability at the end someone among them got the virus is again high. Mm-hmm. So it's just these 2 scales, but they're related in some sense.
Yeah. I think that real dynamics is closer to one extreme, and Italian dynamics is closer to the other. They kind of, I don't know. It would be interesting to perceive, instead to monitor the people, to perceive the signature from the data. You see, like I don't know, I don't know if maybe if comparing 2 towns of the same size and see, I don't know how this can be done, but it would be interesting.
There are data from Google, but also Apple, how people change their behavior, social behavior during the pandemic, the lockdown. So you can check that they went less often to the school, of course, to the workplaces, to the shops. And so this can be used in some sense to do this data. But there are also data that are taken from mobile phone, where they have, okay, of course, mobile, you are not for sure close, because you can phone to someone which is
or not, because actually I've noticed that during some restriction here, people go more often to the supermarket, because supermarket became the happening place where people could meet.
Okay.
So you close to some path, but you create some new path where actually you know. So yeah, so it's interesting, but you're right. You know, you create a new network and new nodes. So the supermarket became a node, because people is the only place where now people meet. You know, and they don't go to cinema. They don't go to. And in fact, actually, one time I noticed, I was looking at the detailed data from one neighborhood I will not mention because people would get scared. Yeah, and I've noticed that in one street, I've noticed that some cases, a lot of kids they were living nearby, and so I started looking. I said, how come people are like, they're not in the same building, but 3-5 minutes from each other? So I look at the map, and I noticed that there was a supermarket. So yes, so it's a new place. But anyway, okay. So thank you very much, and it will be good if we have the slides. So actually, even
okay. I can send you the first part of the slide up to this one.
Yes.
Okay.
So people can review and actually
of course.
to see the books that you mentioned before the next lecture. That would be great. Thank you. So I'm sorry I took all the questions. People want to ask questions. Let's thank Timoteo for this lecture before I forget. So
I was going to say that we didn't thank
you.
So someone has question? No?
Yeah, I have a very silly question. It isn't, you don't have an example that it is worth to think of an infinite network, because when you think about these examples, well, I actually want to go think about another thing that not COVID. We just think about this, but it's really nice to model COVID, but is it possible to think about something that we want to study that could give an infinite graph?
Yes, so let me just draw one picture to explain you. As again, this is something that I would like to present in the last lecture. So I told you about this adjacency matrix. So if you take a network where each node is each node is connected to its neighborhood, say some distance k. Okay, so this means that two nodes are connected among them if they are k friends apart. So if you do the matrix, if you compute the matrix is something like this. You have a band of ones, so they are all ones, and all zeros. So this is n times n. Now you can think, okay, let me go n to infinity. What up? Okay, you don't have any longer a matrix because n goes to infinity, but you can define a function wxy, which is a Wohl's graph, if you want in 0, 1, is something like this. So 1 and 0. And so now this function is the probability that, so W is the probability that node X and node Y are connected. But now nodes is a continuous, so it does not exist really a node. So using this W, you can use what I told you at the beginning, this graph phone idea. So where you have an infinite number of nodes, there are so many nodes that you can compute them as if it was a continuous of nodes. So what is important? The point is that, so yeah, I put a very simple example, but this can be done in more complex one. The point is that, first of all, if you have a function, you can work in functional spaces. So yeah, all a branch of functional analysis is very good. Second point is that, okay, even if I have this kind of function, if now I draw or I select n equal to 1 million, I have a network, this one, which in some sense can behave similar to the limit. And so if you can prove a result that say that if n is large enough, my finite size system behaves close enough to the limit, then you have a result going from infinite dimension to finite dimension. And the last point is the result very recent, that once you have a network of friendship and so on, there's a problem of privacy, because if I know all the friends, so if you think of a mobile phone, if you know all the friends that I have, it's quite easy to know also friends of friends, because of this idea that they call each other. So once you have a network, you lose this privacy. But if you have a matrix where the number of nodes is infinity, in some sense, you can, I don't know, embed this privacy into the continuous in such a way. So I give you the matrix, you don't know exactly who are the nodes, but then you can sample one possible network from this matrix, from this function if you want, and then you lose completely the identity of the nodes. So if you want, this W is a way to pass information about social network without going against the privacy. So this is a recent result where people using this idea to really overcome this problem.
Very nice, very nice. Thank you.
Okay, so other question? Oh, oops, I see one second.